which is modeling the Earth with Fatiando a Terra, and this is Leonardo Uieda. Yeah, did I pronounce that right? I probably butchered it. Okay, thank you very much.
Thank you. Thank you for coming. So today I'm going to talk about this project I have called Fatiando Terra, which is Portuguese for slicing the Earth. And I'm using that to do geophysical modeling. I'm a PhD student from the Observatorio Nacional in Rio de Janeiro. So since everybody has been doing this, so I put my slides on GitHub as well. If you go to the URL, you'll be able to see the slideshow. Since probably most or all of you are not geophysicists, so I'm going to have to talk a bit about geophysical modeling. So the goal of that is to understand what the Earth's structure is and how Earth processes work and what's going on beneath the surface. But unfortunately, we can't really look inside, except for very shallow wells, which go up to at least 15 kilometers or something. We can't really know what's inside. So the way we do that is with indirect measurements. So for example, we can measure disturbances in the gravity field and try to infer what density changes cause that. And we can measure earthquakes, which have traveled inside the Earth, and so they bring information from the Earth structure to the surface. We can measure heat maps that come, so the heat flux depends on what materials are in the crust and all sorts of other measurements. And as an example, let's consider that we have this body in brown, which has a different density from the surrounding rocks. So that body would cause an anomaly in the gravity field, which we can measure. And so the idea then is, how do we go from the gravity anomaly to try to estimate a density distribution? So the way we do that usually is we substitute a complex geometry by simple geometry. So in this case, I used rectangular prisms, and so we try to run an inverse problem to determine the density structure. So then, as I said, this is an inverse problem, so it involves a lot of linear algebra like that. If anybody's familiar with machine learning, you've probably seen this equation before. This can get very big very fast when you have a million or more model parameters. It also involves a lot of numerical modeling, like solving differential equations with finite differences, finite elements. We have to do a lot of numerical integration. We have to work with arrays and all sorts of things. And the way this is typically used to develop a new methodology, which is the way I used to do it, actually, is you start by first writing some C or Fortran code, which would probably be copy-pasted from other software that you did. Then you'd have this part, a part for computation, some part for the I/O, and this is my own code, so I can talk bad about it. And so it's not very simple. You spend a lot of time doing the I/O, and then you write an input file, which is usually a custom format that no human could read. So if you just look at that, I have no idea what that input parameters are. Then third, you'd go on, run your software, and go plot it in 2D or 3D. And you'd usually go about that, go to a tool like ParaView, or the generic mapping tools is very popular in geophysics, or Matlab or Surfer, which are proprietary. But don't get me wrong, I have nothing against the software. They're great software, particularly the generic mapping tools is amazing. If you do any kind of map plotting and you haven't seen it, check it out. But the problem is that this whole workflow is a bit tedious, and it's fragmented, so you have to use many different tools to accomplish what you need. It's usually done by hand. When I was plotting in Surfer, I'd have to go through several different menus just to get a counterplot. And then 6 months later, when I haven't seen this for a while, you can't really reproduce it because you don't know the steps anymore. So this is the way that it's actually done by some people still in my department. And I used to do this up to some time ago. But the problem is that I'm very lazy, so I don't like doing that all by hand. So I decided to create this project that I ended up calling Fatiando Terra, in an attempt to try to automate as many common tasks that I encountered during my research, and try to integrate everything in a single tool so that I wouldn't have to waste my time going through one tool to the other. I tried to expose it an API so that I could develop on top of the things that I had already implemented, and also so that I wouldn't have to repeat myself, and try to make things more reproducible. So the idea is that everything in the modeling pipeline should happen inside Python. So instead of writing new C or Fortran code and copy pasting, I would just write some new Python code, which would be pretty simple. This is a code sample from something that happened during my research for my PhD. So this is inside Fatiando Terra. This was the topic of an expanded abstract, so this function itself. So that's pretty simple. I wouldn't have to worry about I/O because I can use low text, I can pickle, I can use JSON. Then my input file would not be an input file itself. It would just make a Python script that calls the functions that I need. So for example, this is a real example. This slideshow is a notebook, in case you haven't noticed. So then I can just, if I want to create, for example, I want to calculate the gravity field caused by a prism model, so a 3D prism model. I can just call the prism class and make it, give it some density, which Fatiando Terra handles physical properties as dictionaries. So I could give it also a magnetization, I could give it a thermal conductivity, and so on and so forth. Then I can call the gritter scatter function to generate some random set of points. And I can use the gravmag module to calculate the gravity field here, which is GZ. I can just call it on the model and the data points, and I would have the modeled gravity anomaly that I would measure. And then when I go on to plot this result, I can just continue on my same Python script and just use the X, Y, and G that I calculated in the previous cell, and I can just make a contour map out of that. So you'll notice here that I'm using a module called MPL. This is a module that loads everything from Matlab and overrides a few functions to make them easier to call. So for example, if you're familiar with Matlab, you'll know that contourf requires 3 matrices or 2D arrays, and they would need to be regularly sampled, so I couldn't handle scatter data. So something that I had to do all the time was create the arrays, interpolate them, and then make them into 2D arrays, and then pass it to the contourf. So that was a bit tedious. So what I did was just overwrite the contourf function to get 1D arrays, which is what I handle natively. Just pass to it a shape, which in this case is 100 by 100, and tell it interp equals truth, and it'll automatically interpolate it and pass it to the matplotlib contourf. The other functions, the plot and color bar, are the same as in matplotlib, so you get all the matplotlib functionality plus a few extra. So that way I can quickly generate a plot. And also if I want to do 3D plots, I can just continue on the same script and call some wrappers to the Mayavi MLab module, which I wrapped in this MYV module. So if I want to plot prisms, I just call MYV prisms and give it a list of prisms, and it'll automatically convert that to TVTK, which Mayavi uses, and send it to the Mayavi GUI. I have some utilities to plot walls on the bounds, like for example here I plot a wall on the north side and a wall in the bottom. So this is useful to get a better feeling of depth in the 3D model. So the whole pipeline then is inside a Python script, or even better, an IPython notebook. So I can easily reproduce that. I can just rerun the Python script or re-execute the cells. So I can reuse the code without having to copy and paste because I have this API. I can make easy plots because I automated a lot of the common tasks that were annoying. And it's NumPy powered, so it's pretty fast. And the parts that I couldn't make fast with NumPy, I just did some Python code, which is very little, actually. So what's currently available, I have a package called Fatiando. It has many different sub-packages and modules. So far, most of the development has been made in the gravity and magnetics package, which is what I do research on. So that's what I have the most time to focus on. So I can do 3D inversion, fast Fourier transform processing of potential fields. Can do modeling. There's a technique called equivalent layer, which is still in high development in geophysics. So we have that. The Seismic package has just a few toy problems. There is a finite difference solver for 2D elastic wave equations, which is not, it's not very fast yet, but it's already useful. I'll show an example later on. And there's just a simple geothermal example. So a lot of this was developed during courses that I was taking and stuff. So if I wanted to get a better feeling for some problem, I'd just go and implement it. So it's not very ready, but there is some functionality available. Then I also have a mesher class, that mesher module that handles the geometric elements, prism meshes, and so on. I have Gridder for grid generation and interpolation. There are some utilities, the physical constants that I need to use, some input-output, and the visualization. And I'm working on an inversion framework, which is still a bit experimental. So prism meshes are something that, that I use a lot for doing 3D inversion. So for example, I can create a prism mesh, which I just give it some bounds, which are the north, south, top and bottom, east and west. Give it a shape, and I can add physical properties to it as 1D NumPy arrays. And then I can just call the MYV prisms on the mesh. So this mesh, it behaves as a list of prisms. It's not really a list of prisms because that would be, consumes a lot of memory. So this generates prisms on the fly when you iterate over it. So I can also do a mesh with topography, which is something that I usually need to do. If you have a complex region that you're modeling and you have topography, you need to take that into account. So here I can use the utils Gaussian 2D function to generate some synthetic heights. And I can just call the carve topo method, which interpolates the heights on top of the mesh cells and masks the mesh, the cells that are above the topography. So this way I can easily do topography. There are tesseraoids, which are spherical prisms. So when you need to model something that's very large scale, I can't consider that it's a flat Earth anymore. I need to take into account that it's curved. So I can create tesseraoids, give them physical properties. I can plot them in Mayavi with the MYV tesseraoids. I can also plot continent lines, meridians, parallels, the Earth. There's also a function to plot the core, so if you need to do deeper models of the Earth. And I can calculate the gravitational fields of tesseraoids as well, which is an open field of research. This is part of my PhD thesis. It's still a bit debated how it's best to do that. So I can do that using the GravMag tesseraoids module. And I can plot that with map projections using the base map toolkit. So setting up the base map is not the easiest thing. So I was always doing the same things. So I decided to create this MPL base map function. So you give it an area in longitude, latitude, and it already sets up the projection for you, the base map instance. And then you can just pass that base map instance into the contour-F or p-color or contour functions, and it automatically interpolates the data and calls the appropriate function in the base map. So it's basically the same thing that I would do if I was plotting in normal without projections. I just have to pass in the base map. And this is also something that hopefully will be useful for teaching. And this is a recent example that I just developed. So this is how I learned seismic waves when I was in doing my bachelor's. So I'd be shown this seismogram, and then the professor will say, okay, imagine that you have a crust here on top and a higher velocity mantle below. And suppose an earthquake happens there on the red and yellow star, and I have a recording station there in green. So then what I'd be showing is that, okay, I have a refracted wave which travels along the interface, refracting at the critical angle, so that arrives first because the mantle has a higher velocity. Then you have a reflected wave which arrives later. And then you have the surface waves which come on the surface. But this is not very intuitive. When I think about waves, I usually think about this, not those straight lines. So I imagine ripples in water. So then I implemented this finite difference solver just to get a feel for what these waves look like. So I'd much rather teach like this. So I can show here, okay, you see the refracted wave is traveling along the interface, and it travels faster, so it overtakes the main body wave. And there's all this energy that gets trapped in the crust. So the first event that you saw there is the refracted wave. And then after that, you get this whole bunch of energy that creates the surface waves that you measure. So that's why they have a big amplitude. They get trapped inside the crust. The crust acts as a waveguide in this case. So then after you see that, if I show you a real seismogram, it's not going to be so hard to understand. You saw how that happens. You saw why there's all this amplitude that arrives later because it got trapped in the crust. So this gives much better insight into the problem. Also, this can be done fairly interactively. I can just draw a PNG image. For example, this is the crustal model that I used. And I can load that with the from image function of the I/O module and convert that to a physical property like density and pass it to the finite difference solver, and it already runs like that. And the solver is pretty fast, so it can do these things. It can plot and animate as it calculates. So in conclusion, I started developing all this just to automate the common tasks that I encountered doing my research. So this ended up being an API for modeling, which I hope can help other people as well. It might be a useful tool for teaching and also for learning, because I learned a lot when I implemented all these things. I use it for my own research. So my master's and PhD stuff is all in the package already. And mostly because it makes my life easier, so that's why I like it. So for the present and the future, the current modules that I have, as I said, it's mostly focused on gravity and magnetics. I hope to expand the seismic package more as I try to get more collaborators, and the geothermal package as well. So for the future, we want to have more models, maybe work a bit more on the inversion framework, improve the documentation, which is present, but it's not very thorough, and try to get some kind of developer community around this. So I already have some of my friends that started working on this, so maybe that can build more and make more people's lives easier. Just to give a sense of the open source landscape in geophysics, there are a lot of great open source packages. This is not, by far, not the only one and not the most complete. The Madagascar package is amazing. It was presented here last year, I think, by Sergey Fomel. You should definitely check it out for reproducible documents. They have amazing support. There's OpenDetect, OpSpy, SAC. There's the computational infrastructure for geodynamics, which is a great project, and C3 as well. There's a Wikipedia page which has a list of open source software in geophysics if you want to check that out. Also, all the code is developed on GitHub, so if you go to the first URL, you can see all the code that we have. The slides are on GitHub repo as well, and you can go to the homepage for more information, and there will be a blog post about this soon. So thank you very much. questions? Yes? Okay, okay, so the question was, what are tesseraoids geologically? Geologically, they are nothing exactly, just like prisms are nothing geologically. So the idea is if you have small enough tesseraoids, you can approximate a complex geological feature, something like a subducting slab or a mantle plume or something very large scale. If you use very small tesseraoids, you can approximate the complex feature by the tesseraoid model. It's just that you can't really calculate anything from a very complex model, but tesseraoids I can compute, so it's an approximation. Yes?
I saw some of the documentation. Are they similar to quantum physics? Are you using some of the functions of quantum physics? Or
Okay, the question was whether I use Seismic Unix for the wave propagation. The answer is no. I haven't used anything from Seismic Unix. I implemented that more as to get a feel for finite differences and test it out. So it was more of an experiment than something for real use. So it's not parallelized or anything, but it is a bit stable. It uses a method published last year called the equivalent staggered grid, which was applied to the acoustic wave equation, but I implemented it for elastic wave, and it works. So, yeah. Yes. Sorry, I didn't. Ah, okay. So the question was, when I pass interp equals true, what happens under the hood? What happens is that I call the matplotlib grid data function. So I just pass it on, and it returns the arrays, and I just pass it to the contrf function. Yeah, I think isn't it nearest neighbors, or okay. So nobody else?
Thank you very much.
Okay.